the reaction quotient Q. The reaction quotient Q is the equilibrium expression, but when the system is not necessarily at equilibrium. That is, the mass action expression, the ratio of the concentrations of products over reactants, is equal to Q unless we are at equilibrium when it is equal to K. To calculate Q, simply substitute the given values of the concentrations into the mass action expression. Q is used for two important things about the current conditions. 1. It tells whether the system is at equilibrium with the given conditions. And 2. If the system is not at equilibrium, it tells which direction the system must move to reach equilibrium. To determine this, we calculate the value of Q and compare it to the given value of K. If K is found to be equal to the calculated value of Q, then the system is at equilibrium. If K is less than the calculated value of Q, then there are too many products, and the reaction must move to the left to make more reactants to reach equilibrium. Note that if we put K first, then the less than sign points to the left, the direction the reaction must move. If K is greater than the calculated value of Q, then there are too many reactants, and the reaction must move to the right to make more products to reach equilibrium. Note that again, if we put K first, then the greater than sign points to the right, the direction the reaction must move. Calculating Q is a simple way to determine the condition of the equilibrium when we have all reactants and products present. When one or more reactant or product is not present, then that will determine the direction the reaction must move, since we must have some of every reactant and product. Doing calculations involving equilibrium systems is one of the most important areas in chemistry. Let's begin with a fairly simple calculation, calculating the value of Kc. Here is the problem. A closed system initially containing 1.000 times 10 to the minus third molar H2 gas and 2.000 times 10 to the minus third molar I2 gas at 448 degrees Celsius is allowed to reach equilibrium. Analysis of the equilibrium mixture shows that the concentration of HI is 1.87 times 10 to the minus third molar. Calculate Kc at 448 degrees Celsius for the reaction, which is H2 gas plus I2 gas in equilibrium with 2HI gas. In order to calculate the value of Kc, we need to know the equilibrium concentration of each of the three substances, H2, I2, and HI. We are given the initial concentrations of H2 and I2. The initial concentration of a substance is the concentration of the substance before any reaction takes place. From the reaction, 1 mole of H2 and 1 mole of I2 react together to produce 2 moles of HI. The last piece of data we are given is the equilibrium concentration of the HI. There's going to be a lot of information in this problem, some of which is clear and obvious, and some of which is not so clear or obvious. It is very helpful to keep things organized, and to do so, we use what is called an icebox. Using the icebox. The I in icebox stands for initial conditions. The C stands for change in conditions, and the E stands for equilibrium conditions. To set up the icebox, we make a separate column for each reactant and each product, making note of where the separation takes place. Fill in the known information for each reactant and product. In this case, the initial concentration of H2 equals 1.000 times 10 to the minus third molar. The initial concentration of I2 equals 2.000 times 10 to the minus third molar. and the equilibrium concentration of HI equals 1.87 times 10 to the minus third molar. Since nothing is mentioned about HI being present before the reaction occurs, the initial concentration of HI equals 0. Since the equilibrium concentration of HI is 1.87 times 10 to the minus third molar, and we started with a concentration of 0, the change in the concentration of HI is plus 1.87 times 10 to the minus third. Since the product has increased, each of the reactants must have decreased, in this case by half the amount the HI increased, because the coefficients for H2 and I2, 1, are each half the coefficient for HI, 2. Each decreases then by 9.35 times 10 to the minus fourth molar because of the 2-to-1 stoichiometry ratio. These changes are entered in the C row. Note that the changes for H2 and I2 are both negative because the concentrations decrease. The key connection is that the equilibrium concentration is the sum of the initial concentration and the change in concentration. E row equals the I row plus the C row for each substance. We are now able to determine that the equilibrium concentration of H2 equals 1.000 times 10 to the minus third minus 9.35 times 10 to the minus fourth equals 6.5 times 10 to the minus fifth molar, and the equilibrium concentration of I2 equals 2.000 times 10 to the minus third minus 9.35 times 10 to the minus fourth equals 1.065 times 10 to the minus third molar. Now we know the equilibrium concentrations of the three substances, H2, I2, and HI, and we are ready to proceed to the actual calculation. To complete the problem, we substitute the three equilibrium concentrations, the bottom row in the table, into the equilibrium expression and calculate the answer. The concentration of HI is 1.87 times 10 to the minus third molar. The concentration of H2 is 6.5 times 10 to the minus fifth molar, and the concentration of I2 is 1.065 times 10 to the minus third molar. When we do the calculation, we get Kc equals 51. There are only 2 sig figs here because the concentration of H2 has only 2 sig figs. One final point. The most important thing to remember when doing equilibrium calculations is this. K is only equal to the mass action expression when the equilibrium concentrations are used.